Welcome to theastrodynamics.com and theastro.com. This website promotes the right way to build a commercial space catalog. The Astro has developed the analytic perturbed algorithms needed for rapid and automatic commercial space catalog building. This website is not funded or supported by or related to any government. The opinions expressed in this website are purely based on decades of research. Hi, I am Jim Durr. I am an astrodynamics algorithm co-developer. This website has many self-contained videos for catalog building. If you are familiar with any of the topics, you may skip to other videos of interest. This video presents the overview of initial orbit determination (IOD) algorithms for rapid space catalog building. Again, if you are familiar with IOD, you may skip to other videos of interest. This video presents the overview of optical and radar IOD to provide preliminary understanding of 4 IOD topics. 1. Input and minimum accuracies of radar and optical observations. 2. The Astro analytic optical and radar IOD algorithms and their applicable orbit regimes. 3. Output of IOD is the initial state vector at the first observation time for input to DC. Orbit propagation is required if output of an IOD algorithm is at a different observation time, such as that of Gauss or Laplace optical IOD. For example, the Gauss and Laplace optical IOD algorithms outputs the state vector at the second of the 3 observation times. 4. Key optical and radar equations and how to deduce the initial state vector as input to DC. Again, the initial state vector for DC is normally chosen at the first observation time of IOD, which may not be the same as the output of an IOD algorithm. The Astro promotes commercial SP-type space catalog building with analytic IOD and DC algorithms to process observations collected by Earth or ECI ground-based sensors. For the two-body Gauss or Laplace optical IOD, only 3 observations are chosen from one track. For the two-body multi-web Lambert or radar IOD, only 2 observations are chosen from one track. One track of observations should contain reasonable number of observations and sufficiently long time span. With this prerequisites, IOD and DC may be successful. The purpose of orbit determination is to deduce the DC state vector at the first observation time T1 for batch DC as shown, or DC state vector at the last observation time Tn for sequential DC by extended Kalman filter, not shown in this picture. The Astro has developed 8 analytic IOD algorithms, 7 optical and 1 radar, to process observations collected by Earth or ECI ground-based sensors. Again, the output of IOD is the initial state vector at the first observation time for input to DC. Source codes and real-world numerical examples of the two-body Gauss and Laplace optical IOD algorithms 1 and 2 and the two-body multi-web Lambert or radar IOD algorithm 8 are included in my book, Astrodynamic Algorithms for Rapid Space Catalog Building. The key equations and how to solve for the initial state vectors of all 8 algorithms are described in this overview video and the optical and radar IOD videos in various details. The 8 Astro IOD algorithms, 1 to 8 highlighted in red, are ECI based, and the ECI initial state vectors are deduced from observations collected by Earth or ECI ground-based sensors. The MCI-based Gauss algorithm in green and SCI-based Gauss and Laplace algorithms in blue produce respectively MCI initial state vector and SCI initial state vectors using observations collected by ECI ground-based sensors but functioned as space-based sensor input in the MCI and SCI IOD algorithms. MCI in green and SCI in blue IOD algorithms are outside the scope of commercial space catalog building. The two ECI-based IOD algorithms, 1A and 2A, highlighted in red, deduce the ECI initial state vector from observations collected by ECI space-based sensors or sensors in orbits around the Earth. These two IOD algorithms, which were only developed with limited number of test cases, are outside the scope of commercial space catalog building. The two terrestrial SCI-based Gauss and Laplace algorithms in blue, which produce SCI initial state vectors using observations collected by Earth or ECI ground-based sensors, are also outside the scope of commercial space catalog building. Commercial space catalog building concerns about objects in ECI or geocentric orbits, and at least 90% are in LEO in 2023. The 8 terrestrial analytic optical and radar IOD algorithms, 1 to 8 using observations from ECI ground-based sensors, and 2 analytic optical IOD algorithms, 1A and 2A, using observations from ECI space-based sensors, aim to deduce ECI initial state vectors as input to DC. These 10 analytic IOD algorithms are not for MCI in green or SCI in blue applications. The applications of ECI, MCI, or SCI-based IOD and DC algorithms depends respectively on the objects in geocentric, selenocentric, or heliocentric orbits. For example, if ECI-based IOD algorithms are used to process observations from an object in a MCI orbit or SCI orbit, then the computed IOD and DC state vectors will be erroneous or unreasonable. Accurate IOD starts with accurate observations. Accurate observations with field of view resolution of sub-arc second or greater than 5 digits beyond the decimal in degrees can be collected from 3 groups of optical and radar systems. 1. Expensive systems, from the $110 million Optical Space Surveillance Telescope, SST, to the over $1 billion Space Fence Radar. 2. Less expensive systems of the multi-million-dollar Geode and Starlink. 3. Commercial optical systems of $100,000 or less in 2023. Terrestrial IOD and DC algorithms have been able to deduce consistently accurate state vectors from commercial optical systems using real-world observations from LEO to GEO, ex-GEO to cislunar and beyond. However, expensive and less expensive systems are needed and useful for precision applications. In general, given reasonable optical observations time span, observations that are greater than 5 digits beyond the decimal in degrees are accurate enough for accurate IOD and DC algorithms. First, US Air Force B3 input format of optical observations. The decades-old US Air Force B3 format has restricted accuracy to 4 digits beyond the decimal in degrees. However, in year 2023, many inexpensive commercial $100,000 or less electro-optical EO systems can provide accurate optical observations of 5 or more digits beyond the decimal in degrees. In many IOD and DC test cases with shorter time spans, observations of 5-digit accuracy can produce more accurate IOD and DC state vectors. An important rule: the higher the observation accuracy, the shorter the observation arc or observation time span. That is, optical observations of 4-digit accuracy require longer time spans. In general, accurate optical IOD algorithms require at least optical observations of 4-digit accuracy with reasonable time spans. Second, propose free input format of optical observations. To improve optical IOD and DC accuracy, the proposed free format of optical observations that takes advantage of 5 digits or more accuracy is recommended. The ASTRO has built over 10 optical ECI-based IOD algorithms to process optical observations with different observation accuracies, short or long arc or time spans. Observations separated in seconds, minutes, or hours from LEO to GEO, XGEO to cislunar and beyond. Note that an optical observation file contains satellite ID, sensor ID, time, right ascension, and declination. Can you figure out the first observation of the US Air Force P3 input file? It is clear in the proposed free input format file. One optical observation contains 2 angle measurements, right ascension alpha and declination beta. To deduce an optical IOD state vector or an orbit, the inputs are 1. Ground sensor LED long altitude, LLA, or space sensor position vector. 2. 3 sets of accurate optical observations, alpha and beta, or 6 angle measurements in reasonable time span. Proper data collection and advanced optical sensors give respectively reasonable total time span and accurate angles of field of view resolution less than 1 arc second or 5 or more digits beyond the decimal in degrees. In turn, the 3 accurate coefficients A, B, and C of the Gauss and Laplace 8th degree polynomial equation can be computed. See Volado. The output is the correct route or range from the Earth's center, x, which gives the two-body initial state vector or the two-body orbit at T2, and then the IOD state vector at T1. A few typical Gauss and Laplace 8th degree polynomial equations in ECI and SCI are depicted in this picture. After the inputs are processed, the 3 coefficients A, B, and C of the Gauss and Laplace equation, f of x becomes one equation of one unknown, x, which is the range at the second observation time T2. If the observations are real, then the coefficient C is always negative, and only the coefficients A and B can change signs, resulting in 4 combinations. Descartes' rule of signs indicates that the first 3 combinations can only have 1 positive real root, and the problem is solved. The 4th combination indicates at most 3 positive real roots. When there are 3 positive real roots, picking the correct root out of the 3 has been puzzled since Gauss in 1809, but solved by De Astro and included in the professional version of De Astro algorithms. Note that the coefficient C can be 0 theoretically, but the observations are not real. The video of IOD algorithms for rapid optical data processing describes how to solve the Gauss and Laplace 8-degree polynomial equations and other angles-only algorithms. The source codes of Gauss and Laplace algorithms can be found in my book, Astrodynamic Algorithms for Rapid Space Catalog Building. Radar observations are usually more accurate than optical observations, not to mention weatherproof, and therefore radar IOD and DC state vectors are usually more accurate than those of the optical. If accuracy is important and causes no problem, radar observations are much more desirable. A typical radar observation file contains satellite ID, sensor ID, time, range, azimuth, and elevation, and a range rate. Range is usually at least an order of magnitude more accurate than the angles. That is, if range error of radar observation is 10 meters, then azimuth and elevation errors are about 100 meters. The ASTRO has built an advanced multi-web Lambert IOD algorithm to process radar observations to produce state vectors of circular, elliptic, parabolic, and hyperbolic orbits. Note that the proposed new free input format takes advantage of observation accuracy with 5 or more digits beyond the decimal in kilometers or degrees. One radar observation contains 3 measurements: range, azimuth, and elevation, RAE, usually defined in topocentric coordinates of east, north, up, ENU system. To deduce a radar IOD state vector or an orbit, the inputs are 1. Ground sensor let long altitude, LLA, or space sensor position vector. 2. 2 radar observations in RAE or 6 radar measurements. The output is the two-body initial state vector or the IOD state vector at T1, computed by the ASTRO two-body multi-web Lambert algorithm. Transformation of ENU state vector to or from ECI state vector is straightforward, and the source code can be found in my book, Astrodynamic Algorithms for Rapid Space Catalog Building. Note that range-only IOD is beyond the scope of this video. The Sun's two-body multi-web Lambert equation, which can be found in the 1979 AAS AIAA paper of Sun and the 2011 Amos paper of Durr, are solved by the Laguerre iterative equation with the use of the variable Laguerre parameter, the lowercase n. The Sun's multi-web Lambert equations produce 2n plus 1 possible solutions or orbits. The uppercase n is the number of orbit revolutions. The source code of the two-body multi-web Lambert algorithm, XLAM, can be found in my book, Astrodynamic Algorithms for Rapid Space Catalog Building. The two-body multi-web Lambert algorithm, XLAM, which is designated as IOD algorithm 8, can be extended to a perturbed multi-web Lambert algorithm in 3 steps. 1. Solve the two-body multi-web Lambert algorithm for the 2n plus 1 possible Lambert solutions, where n is the number of orbit revolutions. 2. Pick the correct two-body Lambert solution out of the 2n plus 1 possible Lambert solutions. This century-old challenge is solved by the ASTRO and included in the professional version of the ASTRO algorithms. 3. Compute the perturbed multi-web Lambert solution using the correct two-body Lambert solution and Winty targeting as described in the 2011 Amos paper of Durr and the 2015 AAS AIAA paper of Durr. In 1801, Gauss invented IOD and DC to process Piaggi's observations, and in 2022, the ASTRO process 10 optical tracks of Artemis 1 observations. These two examples show that for over 200 years, optical and radar IOD are deterministic. Any probabilistic IOD and DC are misleading. The optical IOD challenge was suggested by Gauss in 1809 that the multiple roots must be reconciled. See page 140 of Bettin's book. However, the class rule of science reduced multiple to 1 or 3 roots. If there is 1 root, the IOD problem is solved. If there are 3 roots, then picking the correct root can be difficult. However, Jim Durr was benefited from the humble reminder of his master's and first PhD thesis advisor Ted Adambaum that he can only solve simple problems. That is, picking the correct root is a simple problem. The radar IOD challenge is to pick the correct two-body Lambert solution out of the 2n plus 1 possible ones. However, Jim Durr was benefited from the observations of the working habit of his second PhD thesis advisor, Dick Bettin. Bettin and his 2 students solved the multi-rep Lambert problem via Gauss' Kepler method. That is, two-body Kepler and Lambert solutions are reversible. This video presents the overview or basic consideration of IOD. The optical and radar IOD videos present the how to compute the initial state vectors. The source code of the analytic IOD algorithms 1, 2, and 8 are included in my book, Astrodynamic Algorithms for Rapid Space Catalog Building, which took years to develop, test, and verification with real-world data. Today, many commercial space companies are building their own commercial SP-type or SP space catalog for short. However, if they are using HB4 for analytic propagation, they are also building their second space catalog TLE. That is, they converted the accurate state vectors in the SP to mean orbital elements in the TLE. It is well known that this conversion is not robust and HB4 has singularities, and in turn making automatic cataloging problematic. On the other hand, the analytic SP-Winty method improves efficiency by directly using the accurate state vectors in the SP space catalog for analytic orbit propagation in track association, UCD processing, conjunction and collision analysis, space tour insurance, prediction for future punting, among others. That is, instead of building 2 space catalogs, SP and TLE, only the SP catalog is sufficient for catalog maintenance and catalog building, not to mention the problematic TLE conversion and the use of HB4 become redundant. Also, the SP-Winty method provides not just a second opinion to the TLE HB4 method, but improves and verifies other computer results. I am Jim Durr. Thank you for watching this video of theastro.com.